Now that we've explored the basic sine function graph, we're ready to go back and revisit translations. We've talked about translations in the context of polynomials, exponential functions, logarithms, many different functions that we've encountered. And what we've learned about transformations, we can now apply to the trig functions. So really, in a sense, we're not learning anything new. Now, just as a reminder, notice we've got these first two are classified as rigid vertical shifts. Notice, if we have a function f of x and we add 5 to it, to the outside, that means that our graph will be shifted up 5 units. That's the effect that has. If we subtract 5, the graph will be shifted down 5 units. Without changing shapes, that's why we say these are rigid shifts. A rigid vertical shift up 5 and a rigid vertical shift down 5. Now, notice with this next one, the 5 is inside the parentheses with the x. This means that we're having a horizontal shift to the left 5 units. Notice f of x plus 5, close parentheses, means we're going to the left 5 units. F of x minus 5 indicates a shift to the right 5 units. And those two are called horizontal shifts, and they too are rigid because the shape of the graph is not changed, just its location. So we just pick it up and move it. Now let's look at the first one, the vertical shift. And here we have just a basic graph of sine. And I have the window going from 0 to 2 pi. And what I want to do first of all is look at what would happen to the graph if we added a 2 to the end. Now, first of all, notice that everything, recall these vertical shifts, take every ordered pair and change the y-coordinate. So, for example, we added 2 to the end of this sine function. What that means is every y value on the original sine graph is being increased by 2. So notice, the maximum was at 1, now it's at 3. The sine graph was oscillating about y equals 0, now it's oscillating about y equals 2. Everything has been shifted up 2 units. Now, if we subtract it 2 units, notice everything is shifted down 2 units. Every y value has been diminished by 2. So the max which occurred up here and had a value of 1, it now has been shifted down to have a value of -1. Instead of oscillating about y equals 0, we're oscillating about y equals -2. And this is called a rigid vertical shift. One of our most basic translations. Now let's look at the horizontal shift. And once again, we'll start off with the basic sine graph, except this time I've changed the window a little bit to go from -2 pi to +2 pi because I want it to have a little more room. So instead of going from 0 to 2 pi, I go from -2 pi to 2 pi so that we can see these shifts a little bit, so that the shifts would be a little bit more pronounced. Now, let's first of all suppose that inside the parentheses we have sine x minus pi over 3. This is a shift to the right pi over 3 units. And notice the original graph, this blue, has now been shifted over to the green. And you can notice where it crosses through the origin, now it's over slightly at pi over 3. And I have these marks on the axis to be in pi over 6 increments. So notice here's 1 pi over 6, 2 pi over 6, which is pi over 3. Now let's look at a third shift here, the sine of x plus pi over 3. Now this is a shift to the left, and once again notice this purple. We started off here with the basic sine graph, and now notice it's been moved over 2 units to the left. Now it's at -pi over 3. So it did cross at 0, now it's crossing at -pi over 3. And this is the basic horizontal shift. Now, we want to get away from the rigid shifts, the shifts that don't really change the shape of the sine graph, to those that do change the shape. And we're going to look at amplitude changes. Once again, here is the basic sine graph, and I'm just back to my 0 to 2 pi. And let's suppose that I multiply the function by 2. Well, notice what's happening. The shape of the graph is changing now because every y value is doubled. So we compute sine x, and whatever that comes out to be, we double it. So that would give you a graph that goes higher. So instead of the graph having a maximum at 1, it now has a maximum at 2. Notice, though, that the graph has not been raised up. It's just been stretched. Notice the graph still oscillates about y equals 0. However, it's just taller. It goes up further and down further. Now, let's look and see what would happen if instead of multiplying by 2, we multiplied it by something less than its original, 1, 0.5. If we multiply by 0.5, notice we get a flatter graph. The graph has not been moved. It still oscillates about y equals 0. However, it's flatter. Instead of going up to 1, it goes only to 0.5 and down to negative 0.5. This is an amplitude change. Now notice for this 2 sine x, the amplitude is 2. Sine x, the amplitude is 1. And for 0.5 sine x, the amplitude is 0.5. And in general, we're going to say that the amplitude is the absolute value of the coefficient of sine. So if you're asked, well, what is the amplitude of sine? It's the absolute value of its coefficient. Now the period change. So here's the basic sine graph, and notice I'm going here from 0 to 2 pi. Now what we want to notice about this is, for sine, 0 to 2 pi is one period. That's how long it takes sine to go through one complete cycle. Now we can speed things up or we can slow things down. Notice this. Notice that I multiplied the inside by 2, so now I have sine 2x. Now what has happened now is this sine graph is completing a cycle twice as fast as sine. Notice sine took all the way to 2 pi to complete a cycle. Sine 2x, if you look at how long it takes only pi. So its period is pi. So it completes one complete cycle between 0 and pi, and 2 cycles between 0 and 2 pi. So this 2 in the front tells us how many cycles will be completed in a typical 2 pi period. And you can see that it's going through the process twice as fast. Now on the other hand, let's suppose that we multiply the inside by 0.5. So it's less than 1. Now it only goes through half of a cycle from 0 to 2 pi. And you notice this purple. It only completes half a cycle between 0 and 2 pi. So this is a change in period. Okay. So this has to do with stretching the graph out horizontally, whereas the previous change in amplitude stretched it out vertically or compressed it vertically. This stretches it out horizontally or compresses it horizontally.